Hello everybody, today we're going to be reading Chapter 1 of the Galileo Connection, Resolving Conflicts Between Science and the Bible by Charles E. Hummel. For more than 2,000 years, ancient Greece has captured the imagination of the West. Long after Pericles and Alexander, Greek thought influenced Rome, the Renaissance mainly from the city of Athens, which defeated the Persians in 479 BC and enjoyed a 50-year golden age of cultural vitality unique in human history. Then, after losing a long war against Sparta, its rival city, Athens enjoyed a period of classical philosophy produced by Socrates, Plato, and Aristotle. Before returning to Aristotle, whose thought came to dominate Western science for nearly 20 centuries, we will look at some of the early highlights of Greek science. From the dawn of civilization, people have tried to understand the natural world. The Babylonians developed an interest in the heavenly bodies and kept accurate records of their astronomical observations. The Egyptians worked out a decimal notation and the basic operations of arithmetic. Such activities were carried on for practical purposes like astrological prediction and land measurements. The Greeks, however, pursued knowledge for its own sake, becoming the original sciences of ancient Europe. For them, science and philosophy were inseparable companions. Greek philosophy covered all areas of thought, including music, ethics, and politics. Natural philosophy dealt with the natural world of the earth and heavens. From the outset, Greek philosophy was bound up with mathematics. The early Ionian philosopher Thales of Miletus, ca. 640 to 550 BC, was a mixture of practical scientist and philosopher. He is reported to have originated the science of deductive geometry. Thales earned his place as the initiator of Greek philosophy by conceiving the idea of the unity in difference. He held that all things are varying forms of one primary ultimate element, water. The Milesian school of philosophy was the first to assume that the whole universe was natural. Potentially, it could be explained by ordinary knowledge and rational inquiry. The following century produced a dozen able philosophers who wrestled with the problems of knowledge, substance, being, and change in a variety of ways. Particular interest is Pythagoras, ca. 530 BC, who founded a great religion as well as a scientific tradition. He created a community of men and women that prescribed a simple lifestyle with all possessions held in common, a distinctive costume, and rules for daily living. Pythagoras discarded the idea of one single element. He believed that matter was composed of varying combinations of earth, water, air, and fire. He considered the earth to be a sphere, resting at the center of a spherical universe because he believed the sphere to be the perfect shape. He also considered the sun, moon, and 5 known planets to be spheres with uniform circular motions around the earth. Pythagoras saw order, harmony, balance, proportion, and universal law in the world, which is the key to all of which is mathematics. During the 16th century, a Pythagorean school in southern Italy re-emphasized the importance and religious significance of numbers in understanding the world. The conviction provided an intellectual climate for the acceptance of Copernican views of the solar system. The belief that ultimate reality is found in numbers and their relationships still influences modern science. A Pythagorean named Philolaus taught the Earth moved around the center of the universe like any other planet. Its center was not a sun but a central fire which could not be seen. Philolaus' system, the earliest ever revolving Earth, was later noted by Copernicus when he searched among ancient philosophers for an alternative to Aristotle and Ptolemy. Aristotle, 384 to 322 BC. Aristotle was born in 384 BC in Thrace. His father became the personal physician of King Amyntas II of Macedon, grandfather of Alexander the Great. Family moved to the Macedonian capital and participated in court affairs. Both of Aristotle's parents died when he was a boy. In 367 BC, around the age of 17, he went to Athens to complete his education. There he entered Plato's academy and soon earned praise as the mind of the school. Aristotle remained at the academy for 20 years. Then he began his original studies in zoology, which later earned him a high reputation. Now having strong family ties, he spent much of his time with other teachers, including the orator Demosthenes. When Plato died in 347 BC, Aristotle left Athens and stayed away for a period of 12 years. His reasons may have been both professional and political. The new head of the academy, Plato's nephew Speusippus, reportedly overemphasized the mathematical side of his uncle's teaching. A more compelling pressure might have been the new anti-Macedonian mood in Athens. This middle period of Aristotle's career took him first to a court on the far side of Aegean, where the ruler Hermias, a fellow alumnus, founded a branch of the academy. Aristotle married Hermias' niece Pythias and settled down in a Platonic environment with other distinguished graduates from Athens. 344 BC, Aristotle moved to the Aegean island Lesbos to be near Theopaphros, another academy scholar whose work on plants made him the father of modern botany. The two became lifelong friends. In 343 BC, Aristotle moved again, this time to Macedon, as a tutor to King Philip's young son, Alexander. 3 years later, that former relationship ended as Alexander became regent in the absence of his father on a military campaign. Aristotle probably remained in Macedon for another 5 years, possibly as an informed advisor to Alexander, who became king in 336 BC when Philip was assassinated. The final period of Aristotle's career began in 335 BC when he returned 335 BC when he returned to Athens, now under Macedonian rule. He established his own school on the grounds of the Lyceum, a place already popular with sophists and scholars. Among the buildings was a covered courtyard, parapatos, a walking place, which was possible to carry on a discussion while strolling. From that habit, the students became known as peripatetics. Aristotle built up a natural history museum and a collection of manuscripts and maps that became the prototype of modern university library. Everything he prepared for public reading in Plato's style had been lost, except for fragments and later reports. Most of the surviving documents, a collection of which was edited in the 1st century, are more like notes produced in the course of Aristotle's teaching and study. The research program undertaken by Aristotle and his colleagues far surpassed any earlier achievements. Its scale was a result of his insistence on reviewing the data and common opinions in order to discover the problems and begin to resolve them. This research produced histories of speculative thought, studies of the social studies, and work in natural sciences. Aristotle became the greatest collector and organizer of knowledge in the ancient world. Aristotle taught in Athens for only 12 years. During that time, his wife Pythias died, and he remarried. In 323 BC, Alexander the Great, king of Macedon and conqueror of Greece, friend of Aristotle and patron of the Lyceum, died of malaria in Babylon. An outbreak of anti-Macedonian feeling spawned a movement to expel Aristotle. Faced with the charge of impiety and the prospect of an unjust trial of that like Socrates, he refused to allow Athens to sin twice against philosophy and left the city. The philosopher traveled to Chalcis, where he died a few months later. Aristotle's character can be seen by his will. It made financial provision for his wife, Heracles, including a dowry in which she would remarry. He provided for his 2 children, one by each wife, and bequeathed to his library to Theopaphros, his friend and favorite pupil, who had directed the Lyceum after Aristotle left Athens. He also made good provision for his slaves. Aristotle showed understanding in his dealings with people as well as in his scientific pursuits. Aristotle's universe. Aristotle believed that the universe is finite and spherical, with the stationary Earth at its center. The simplest entities in nature are the 4 elements of which the world is composed: earth, water, air, and fire, each of which is an ideal substance. The center of the universe is a motionless sphere composed of earth, forming the dry land. Over this is a layer of water comprising the ocean. Next comes an atmosphere of air, then comes an outer covering of fire extending as far as the moon. Objects in our world are composed of 2 or more of these elements. For instance, paper consists of fire and earth. During combustion, the fire is released as flames and the earth remains as ash. Observation of his earthly surroundings showed Aristotle that terrestrial bodies are changeable and destructible. They are born and they die. He also noticed that the natural motion of objects on earth is up or down. Since air and fire are light, they move upwards. Because earth and water are heavy, they move downward. Aristotle concluded that natural motion is innate, leading each body to seek its own resting place. He also noted another kind of motion which he called violent. When a heavy object like a projectile is thrown upward, the motion is contrary to the natural downward tendency, so needs a force to sustain it. When that force ceases to operate, the projectile descends, seeking its natural place at the center of the earth. Aristotle concluded that the composition of the celestial bodies differs generically from the 4 terrestrial elements. They are composed of a 5th element, aether, not subject to change or decay, and far superior to the elements of our world. Further, the natural motion of celestial bodies is circular, perfect form with no beginning, end, or limit. Therefore, the ether must be eternal as well as immutable and indestructible. Within his concept of the universe, Aristotle saw all bodies arranged in an orderly hierarchy of perfection, from formless matter at the center to matterless form at the periphery. On Earth, the degrees of perfection range from the lowest inanimate objects up through the plants, animals, and human beings. The living beings have their particular kind of soul: vegetative, sensitive, and rational. The highest matter in the heavens has the perfect form not found on earth. Beyond the outer sphere of the stars is the most perfect being with form and no matter. Clearly, such a cosmology calls for 2 different systems of dynamics. Everything below the moon is controlled by terrestrial physics. Most and elsewhere in the universe is controlled by celestial mechanics. The first system is easier to explain. Since terrestrial bodies rise or fall from the center of the Earth, also the center of the universe, Earth must be resting in its natural place. There is no need of moving, no place to go. Aristotle remarks this view is farther supported by the contribution of mathematicians to astronomy, since the observations made as the shapes change, by which the order of the stars is determined, are fully accounted for on the hypothesis that the Earth is at the center. Although not an astronomer, Aristotle was interested in formulating an explanation for celestial motion. He accepted the theory of concentric spheres proposed by another Academy alumnus, Eudoxus of Cnidus, ca. 401 to 355 BC. The Earth is the center of the universe. The sun, moon, and planets are embedded in their own transparent crystalline spheres which carry them around the Earth. To account for the celestial observations, each has its own major sphere with a nest of helping spheres. The fixed stars, which do not move with respect to one another, are all attached to a single outer sphere that also revolves around the Earth. Enclosing the whole universe is the sphere of the prime motion, from which all motion in the universe ultimately comes. That primary sphere is turned by the first unmoved mover. Thus, the universe consists of a nest of concentric spheres, one within another, and the Earth as a common center. Figure 1. Although short-lived as an astronomical device, the system of the concentric spheres was significant in the development of astronomical thought. During the brief time when it seemed to the most promising explanation of planetary motion, Aristotle incorporated the spheres in the most comprehensive, detailed, influential cosmology of the ancient world. His model was generally accepted in Western thought till the early 17th century. Aristotle's doctrine of the two realms also persisted for many centuries. The sharp distinction between the incorruptible heavens and our corruptible earth took firm hold on people's minds. In fact, it was not completely abandoned until after the time of Newton. Aristotle's science. Unlike many earlier philosophers, Aristotle carefully argued his points on a bias of scientific principles. He gave specific reasons, for example, for believing that the Earth is a sphere, its curved shadow on the face of the Earth in eclipse, on the face of the Moon in eclipse, the sight of the stars not previously visible when one travels south or north. Aristotle endeavored to complete the unity by weaving all of being by weaving all the separate things and qualities into the world into one fabric of thought. To that end, he enumerated 10 categories of how universal properties. For instance, what is it? Substance, animal. How it looks, color, brown. How large is it? Quantity, 30 pounds. Where is it? Place, earth, and so on. What then is a scientific research? For Aristotle, it was to discover an object's universal properties so that it can be properly placed on regular or ascending order of nature. Because quantity was only one of 10 categories, his procedure was more classification than measurement. Since the categories were ordinary perceptions of daily life, Aristotle's science was mainly a matter of describing familiar experiences in concrete form. Scientific classification encompassed not only questions of value but also the concept of purpose, since Aristotle saw a world as gradually approaching a goal. He distinguished 4 kinds of causes. The material cause is what comprised an object, the bricks and wood of a house. The formal cause is the plan or archetype, the blueprint. The efficient cause is the primary source of the change, the builders, and the final cause is the purpose, to provide a home. These 4 causes are the trademark of Aristotelian science. The idea of final cause was the first to come under attack by the new science. Eventually, only the efficient cause remained as necessary for explaining a natural phenomenon or event. Aristotle considered science to be correct thinking based on universal principles. Human knowledge begins with sense perception, observed data, and 2 proceeds inductively to universal principles. Science, then, 3, consists of logical reasoning which derives particulars from those universals. In other words, the work of the observation induction is simply a necessary preliminary to the true science, which is deduction from first principles by reasoning. It is not surprising that Aristotle is known as the founder of logic, which rests on definition and syllogism, the process of proof. What then is the task of science according to Aristotle? Mainly to arrange over the physical world and put things in their proper place within the system Aristotle developed, that is, to discover the qualities of things in order to classify them. Since through action and reaction of the world, governed by a regular process, is becoming a unity and moving toward an end, the scientist is concerned with the final cause or moving of phenomena, as well as their efficient cause or mechanism. Because Aristotle developed so comprehensive a philosophical system into which everything must fit, it became impossible to challenge one feature without weakening the entire framework. Eventually, the scientific revolution of the 16th and 17th centuries challenged not only Aristotle's astronomy but his scientific method. Copernicus's sun-centered solar system, Kepler's elliptical planetary orbits, Galileo's physics, and Newton's universal gravitation rearranged the heavens and unified nature. In the process, they introduced a significantly different concept of science. Nevertheless, Aristotle's influence in Western civilization has persisted in many concepts that continue to determine the structure of our thinking, expressing, and even inquiry. Our philosophy and science will still use as conceptual tools a number of words he coined and defined. For example, category, matter, and form, universal and individual, genus and species, property. More important for science, however, was Aristotle's approach to nature, which was forgotten by the later Aristotelians who bitterly opposed Galileo. It is through observation, aporia, Greek for doubt, reason, and cautious argument that he thought our statements should fit the phenomena. Archimedes, 287 to 212 BC. The influence of Archimedes on Galileo warrants a review of the Greek philosopher's achievements in mathematics and mechanics. His name appears more than 100 times in Galileo's writings. Archimedes was born into an aristocratic family at Syracuse, Sicily, around 287 BC. His father was an astronomer Fidus, possibly a kinsman of King Hieron II, ruler of Syracuse. Archimedes studied in Alexandria, Egypt, where he played an important role in the development of Euclidean mathematics as it became science of its own. For the rest of his life, he exchanged ideas with the scholars he had met in Alexandria. Archimedes returned to Syracuse and there continued his research and composed most of his works. His main interest lay in mathematics, especially geometry. Like later mathematicians such as Isaac and Gauss, Archimedes united theory and application. More than any other Greek, he demonstrated the modern scientific combination of mathematics and experienced inquiry applied to a specific problem. He set forth on a hypothesis, deduced the logical consequences, and tested it by observation and experiment. Two best-known examples concerning floating bodies and levers. Archimedes' principle states a body immersed in liquid is buoyed up by a force equal to the weight of the liquid displaced. Although the lever had been used from time immemorial, Archimedes worked out its theoretical principle. He exclaimed, "Give me a place to stand on, and I will move the earth." Archimedes ranks with Newton as a founder of mathematical physics. His reputation and antiquity was also founded on his mechanical inventions. One of those was the water snail, a screw-like device to raise water for irrigation, which he invented in Egypt. He also devised an endless screw and compound pulley to launch a ship. Plutarch reports that when Hieron asked Archimedes to show how great weight could be moved by small force, the philosopher chose a three-masted merchantman that had been dragged ashore by the great labor of many men. After putting him aboard the customary freight and many passengers, he seated himself at some distance and easily moved the ship with the system of pulleys. For his work in astronomy, Archimedes built an instrument to measure the angles of the rising sun to estimate accurately the length of the year. He also constructed the model planetary spheres, with the relative positions of the sun, moon, planets, and stars to illustrate the Eudoxian system of the universe. Nevertheless, like other Greek natural philosophers, Archimedes looked down on technology. Practical applications of science were acceptable only for agricultural and military projects. In the latter, he excelled with an array of fabulous ballistic weapons used against the Romans. In 215 BC, the Roman general Marcellus marched against Syracuse after it made an alliance with Carthage. Attacking the city by land and sea, he was repulsed by a variety of weapons effective against his ships and his soldiers who tried to scale the walls. Marcellus then besieged Syracuse for 3 years while he conquered most of Sicily. He was finally able to exploit a weakness in the defense and capture the city. During the ensuing battle, Archimedes was killed by a Roman soldier. Greek astronomy. After the death of Alexander the Great, his empire was divided into three separate kingdoms, one of which was Egypt. There, Ptolemy Soter, a son of a Macedonian parents who had served under Alexander, founded a dynasty. As Ptolemy I, he made the new city of Alexandria his capital. He founded a magnificent library and museum, whose first director was Demetrius of Paphron, a pupil of Aristotle and former governor of Athens. Ptolemy had an ingenious method for increasing acquisitions to his library. Every foreign ship coming into port was required to leave copies of its books before departure. About 100 scholars, including Euclid, the famous geometrician, came from all over the Mediterranean area. Teaching took second place to research as Alexandria became the new center of Greek science. Astronomy and mathematics prospered for several centuries, culminating in the work of Claudius Ptolemy. Later, Alexandria became also a center of Christian influence in the Roman world. Chapter 8. Greek astronomy had a considerable history before it became associated with the name of Ptolemy the astronomer, not to be confused with Ptolemy the ruler. Heraclides of Pontus, ca. 350 BC, a complementary of Aristotle, had made steps toward a heliocentric idea of the solar system. He held that the Earth rotates on its axis. Heraclides also taught that when the Sun and major planets revolve around the Earth, Venus and Mercury revolve around the Sun as it moves. His model was the forerunner of the one adopted by Tycho Brahe, Chapter 3. Aristotle of Samos, ca. 310 to 230 BC, came on the scene about 75 years later. He looked at the problems of the solar system geometrically and did some original measuring to determine the distance and sizes of the Sun and Moon. Most significant was his view of the universe. The center is the Sun, around which the Earth and the other planets revolve. The outermost sphere of the Sun is stationary. It appears to move because the Earth rotates daily. Several factors work against the acceptance of uh, Aristarchus' theory. First, the idea that the Earth moved violated common sense, and you would completely see that it was the Sun which moved. Second, it was the absence of any stellar parallax, not observed until 1838. Third, the climate of scientific thought was against such a novel and far-reaching idea. It would have played havoc with the logical system of crystalline spheres taught by Plato, Euclid, and Aristotle. Finally, Arcesius neither worked out his theory in detail nor made use of it to calculate planetary tables. The task was carried out with increasing accuracy by the Alexandrian astronomers using more complex but traditionally accepted model, which soon left Arcesius' idea in the dust. Eudoxus' model of homocentric spheres had been designed to account for the wandering of the planets, their apparent retrograde motions. A planet can seem to stop its movements eastward along the sky, move back westward in retrograde motion for a time before resuming its eastward journey. We now know that the apparent retrogression of Mars, for example, is caused by the Earth's faster movement. When the Earth passes Mars, Mars appears to stop and then move in the opposite direction. To solve the problem, Eudoxus assigned each planet a set of spheres. The other one, carrying the planet like a marble on a rotating beach ball, was moved by the next inner sphere, and so on. For Mars, an adjustment of the velocity and tilt of the four spheres could account for most of the planet's apparent motions. All told, 27 spheres were needed to account for the variations of the planetary motion. In spite of its general success, however, the system had several weaknesses. Because all the spheres were homocentric, with the Earth as their center, there was no way for the planets to approach the Earth or recede and thus account for changes in their brightness. Hipparchus of Rhodes, ca. 190 to 120 BC, made a contribution toward the solution of that problem. We know nothing of his life, and his only two writings to survive are insignificant. Yet the astronomer Ptolemy had the highest respect for his work. Hipparchus was the first to determine the true length of the year and the precession, or gradual moving forward on the calendar, of the semi-annual equinoxes. He also invented many astronomical instruments. Hipparchus prepared a detailed catalog with measured precisions of 850 stars. He also specified their brightness with 6 ranges of intensity, introducing a method fundamentally the same as the one used today. His catalog, modified by Ptolemy, was the one later used by Copernicus. Although Hipparchus is known mainly for his observational work, he gave some thought to the solar and lunar orbits. He represented the motion of the Sun, for example, by a circle not centered exactly on the Earth. That circular orbit, eccentric with respect to the Earth and later called a deferent, allowed the Sun to move with uniform speed and still appear from the Earth to spend more time in the center quadrant than in the winter one. The model preserved the perfect uniform circular motion of the heavenly body required by Aristotle's philosophy. Still, Hipparchus failed to build a geometric model to predict the retrograde motion of Mars and its faster movement in half the sky toward Capricorn. Apollonius of Perga, ca. 200 BC, made an additional step toward the solution of the problem. He placed a secondary circle on the larger one, an epicycle of the different figure. The planet on the rim of the epicycle now traced out and looped path, moving toward, in a way, the center of the different. But the question remained, could this model represent the apparently irregular motion of Mars while still retaining the required uniform motions for the epicycle and the deferent? By the time of Ptolemy's work around AD 135, the accurate representation of Mars's orbit was the greatest unresolved problem in astronomy. Ptolemy, AD 100 to 170. Claudius Ptolemaeus worked in Alexandria between AD 127 to 151. By then, Rome had gained political ascendancy and was ruled by Hadrian, who had a love of culture. Although the library at Alexandria flourished, scholarship lapsed in a reminiscent mood, like the empire itself, as it assessed and consolidated past achievements. Ptolemy's work was affected by that outlook, but Ptolemy was a Greek. His books demonstrate the probing inquiry spirit of his great predecessors. Although he wrote on optics and astrology, Ptolemy made his greatest contribution in the fields of geography and astronomy. A treatise in the 8 sections covered the known world. It was more accurate and comprehensive than any previous atlas. His map of the heavens, on the map contours of Aristotle, said a spherical earth immov- immovable in the center of the universe. Ptolemy considered the possible rotation of the earth, but the best available measurements did not support such a motion. He realized that the astronomical phenomena would look the same whether the earth spun or the stars moved. But he rejected the earth's rotation for physical reason. Objects would fly off the earth, birds would be left behind. Even though he agreed with Aristotle that the earth was the center of the universe, as an astronomer, Ptolemy was concerned to account for the motions of the heavenly bodies in their best possible manner. He inherited the problem of Mars along with the works of Euclid, the observations organized by Hipparchus, and a great amount of astronomical data from the Babylonians. Ptolemy's goal was a calculation of planetary positions at any time, past, present, or future. Using a theorem from Apollonius, he could calculate the size of an epicycle with respect to the deferent, yet reproduce the average retrograde loop, figure 2. Yet the observations still caused 2 problems. The loops themselves vary in size from one retrotransgression to the other. Further, Mars appeared to move 40% faster on one side of the orbit than the other. Ptolemy wondered how he could produce the necessary variations in the loops and the speed in the center of the epicycle. After experimenting with several possibilities, he finally solved the problem by adding an equant, a circle with an equalizing point. In Figure 3, the geometric center of the deferent is the Earth from which the equant point is displaced. The rate of rotation in the deferent is required to be uniform, not with respect to the Earth, but with respect to the equant point. Although the planet moves at a regular rate with non-uniform circular motion, it has uniform angular motion, equal angular movement in equal times. In that way, the philosophical principle of uniformity is preserved from the equant viewing point, although not along the deferent itself. Ptolemy's achievement is remarkable in view of the rough and incomplete observations available to him. Only from Mars are the effects readily seen. Hence, that planet played a key role in his discovery, just as it did almost 1,500 years later in Kepler's calculations. Ptolemy discarded Aristotle's fears and developed a system with the above-noted devices to explain the apparent motions in the heavens. Ptolemy could save the appearances phenomena by mathematically accounting for the celestial observations. In modern terms, he formulated a theory to fit the data. His geometric devices did not necessarily correspond to the reality they represented. That became the crux of the later conflict over Copernicus's heliocentric theory. Was it to be taken simply as a better mathematical tool or a representation of reality? Because Ptolemy's system displaced that of his predecessors, so all successors, including Copernicus, used this model, became known as the Ptolemaic astronomy. He was the first astronomer to put together the deferent epicycle equant model to account for the apparent motions of the sun, moon, and each of the 5 known planets. Ptolemy presented his work in 13 books entitled Great System of Astronomy, which later became known as the Greatest. The Arabic translation of Al-Majesti was changed centuries later to Almagest. Written in Alexandria around AD 150, it is indeed the greatest surviving astronomical work of antiquity, a remarkable synthesis of treatises on theoretical astronomy and a practical handbook. Even though Ptolemy's goal was achieved within the now discarded Earth-centered cosmology of his day, the Almagest is still honored as a timeless classic. More than any other book, it has demonstrated that natural phenomena, complex in their appearance, could be described by relatively simple underlying regularities in a mathematical fashion that allowed for some specific predictions. Such interaction between theory and observation continued to lie at the heart of the scientific method. For the next 14 centuries, the Almagest was considered authoritative. Although they had made adjustments from time to time, astronomers seldom, if ever, looked for fundamental modifications of Ptolemy's technique. He completed a geocentric model of the universe, persisted until a Polish astronomer became exasperated with what he called a monster, and decided a radically different approach to the motion of the sun and its planets.